All right. So we're doing the sample test for calculus, chapter 1. The function over here, we're going to start talking about average and instantaneous rates of change to start with. Here we've got an average rate of change that we're trying to figure out from -2 to 5 here, right? Sorry, 0.5. 0.5. And so in order to figure out an average rate of change, what we're going to want to do is go over here to 0.5 and draw a little dot, this being 1. And -2, we're also going to want to draw a dot here. And then you would essentially take a straight edge and draw basically best you can secant line through these two values here, right? Like this. Mine wasn't very spectacular, but you get the picture. And to find the average rate of change, you're basically finding the rise over the run for this, right? And so I'm just going to estimate this. I've got a run of about 1, 2, 3, 4, 5 of these blocks here, right? And each block is a half of a unit. So I've got a run of 2.5. Oops. Sorry, that would be my run. So my rise over my run. 2.5 is my run. And at the same time, I'm rising actually a negative amount here. So I'm going to go ahead and do 1, 2, 3, 4, 5, 6, 6 or 7. We'll go 7 of these half. So 3.5 is, and it's a negative because it's a run, right? And so you're basically going to get 7/5. It's a negative. All right. That's my rise over my run. Now, for an instantaneous rate of change, you're doing it at a single location here. All right. And so what we're going to want to do here is basically go to 0, which is x value 0 is this line here. Go to the function and draw a dot. And now you're going to attempt to make a tangent line. This tangent line happens to be horizontal. And so it is horizontal. And so therefore the instantaneous rate of change is 0. Note, it's not because it's at x equals 0. It's because it is horizontal. Okay. Here, let's keep moving, investigating further the average rates of change. The average rates of change for x squared plus 2x minus 1. That's what we're trying to do here. Remember, to find the average rate of change from -1 to 1, it's f of 1 minus f of -1 over 1 minus a -1. And so f of 1 is simply 1 squared plus 2 times 1 minus 1 minus f of -1, right? We're doing f of -1 now here. And that is a -1 squared plus 2 times a -1 minus 1. And then again, all of this is over 2. And so, taking a look at this, I've got a 1 minus 1 here. Some things might cancel for us. For example, this 1 squared and this 1 squared, which happens to be negative, remember? Because this negative goes in and changes the signs of all of these things here, right? And so I've got 2 minus 1 left over. 2 minus 1, that's this guy and this guy. And this is a negative 2, so a positive 2. This is a negative 1, and so that is a positive 1. Oh, sweet, cancels with that. And we've got a 2. It looks to be we have a 4 over 2 or 2. That would be your average rate of change. Here we've got an instantaneous rate of change, and we're going to use the same function as provided previously. So it's f of x equals messed that up. It's a 2x squared plus 2x minus 1. Sorry, that 2 is still not there. And in order to find the instantaneous rate of change, you're going to have to use the derivative. And for our purposes, in the early stages of this course, the derivative is written like this. And the theory behind it is that here we've got the run, and here we've got the rise, and so we're talking an instantaneous rate of change. And the reason why it's an instantaneous rate of change is because this this h on the bottom here is approaching 0. So therefore, your average rate of change becomes so small that it covers only an instant. All right. Well, let's go ahead and plug this guy into the instantaneous rate of change finder formula, which is the derivative. And so I'm going to do f prime of x equals x plus h squared plus 2 times x plus h minus 1 minus x squared plus 2x minus 1. Okay. Don't forget parentheses here. All right. And all of this is over h. And don't forget as well that what you're going to want to do is write the limit as h approaches 0. Okay. Now, this is going to take a little bit of work. All right. But that's okay. We'll be able to get that figured out here. So my derivative is still as h approaches 0 of this is x squared plus 2x h plus h squared plus 2x plus 2h minus 1 minus x squared plus 2x plus 1. That was a minus here. All right. So what we're basically doing here is this guy is here, right? And this guy is here. Notice I changed all of the signs there, I think. right? And this is still over h. Let's see what cancels. We've got an 8. These guys cancel. Negative x squared and an x squared. We have a 2x and a 2x, both canceling. Oh, look at that. We have a 1 and a 1. All right. Now, something else that cancels is here you've got an h. There you've got an h, an h, and an h. And so that becomes just a single h. That becomes a 2, right? And so the things that we're keeping our eyes on over here are basically this 2, right? There. This is just a single h that's left over. And then here's a 2x, right? So it's 2x plus 2 plus h. So it becomes the limit as h approaches 0 of 2x plus 2 plus h. And I think we got everything there. Yeah, there it is. And now, basically, if you allow h to be equal to 0, there was an equal sign there that should not have been there. I just erased it because this is the limit of this. Now we basically are making h equal to 0, and so basically this guy becomes 0, and so your derivative is 2x plus 2. This is your derivative. And since we are actually looking for the instantaneous rate at 5, basically I'm doing f prime of 5 equals 2 times 5 plus 2, or 12. And that's basically going to give you the slope of your tangent line there, all right? And that's your instantaneous rate of change. Here we go. Moving on, we studied a little bit on sequences. So the general term of a particular sequence, here it is. Okay, what is the limit of this function as n approaches infinity? Remember that for this one, Tn equals n over n plus 1. If I take the limit as n approaches infinity of Tn here, it's going to be infinity, right? Positive. Oh, sorry, that's incorrect. It's going to be 1, right? The reason being is because the coefficients to this thing are a 1 here and a 1 there. And when the degree of the numerator and the denominator are the same, then the coefficients of the lead coefficients, the ratio of the lead coefficients will give you the limit of the sequence at infinity. That's A. Here's B here. Provide the first 4 terms of this sequence so that we can see what's going on. So term 1 is 1 over 1 plus 1, or 1/2. Term 2 is 2 over 2 plus 1, or 2/3. Notice this is closer to 1 than this, right? Term 3 is 3 over 3 plus 1, or 3/4. 0.75. We're getting closer to 1. term 4 is 4 over 4 plus 1, or 4/5, even closer to 1, right? So this is like 0.5, right? This is 0.6 repeating. This is 0.75. This is 0.8. Notice each one is getting a little bit closer and closer to 1, but the rate at which it's getting closer and closer to 1 is not getting too big. So it will hit 1. Here we've got a limit. Let's do this using algebra, right? Remember, when you're evaluating a limit algebraically, you just go ahead and plug in the value, right? So I'm going to go ahead and just do a quick plug in and see what I get. It appears that I'm going to get, I'll go down on this one, 2x to the 1/2 squared plus 1/2 over 2 times 1/2 plus 1. This is very interesting. I thought it was supposed to be. I might change this actually, because we're going to get here a quarter, right? A half squared is a quarter. A quarter times 2 is a half. This is oh, that was supposed to be a negative in there too, by the way. There we go. All right, so this is a quarter. Because half of a half is a quarter. Because half squared is 1/2 times 1/2. Half of a half is a quarter times 2. This is negative a quarter. All right. Negative 1/2 minus 1/2 over 1/2 plus, sorry, this is 1 plus 1 over 2. Wow, this is pretty boring. And so it's 1/2 and 1/2. Yeah. All right. We'll leave it at that, actually. So this is... Yeah. All right, there's our limit. I think what I was expecting to do is something different. Let's change this this question. Let's do the limit as x approaches negative 1/2 over 2x squared minus x. And then we've got a 2x minus 1. Okay. So basically, with the negative 1/2, oh shoot, there's a positive on the bottom here. There we go. Okay. With the negative 1/2, we actually will get a limit of indeterminate form here. So I'm going to do, excuse me. Where are we at? Oh, there we are. I'm going to do negative 2 times 1/2 squared. This is negative 1/2 minus a negative 1/2 over 2 times a negative 1/2 plus 1. Okay. And now if you look at this, you actually get a 0 over 0, right? Because up in the top here, we are getting a 1/2 squared, but it's negative 1/2 squared, so it becomes positive, right? Positive 1/2 times 2 is a half plus 1/2. This is all up in the top here. Plus another 1/2. These two become positive, essentially. So this is a negative 1/2, positive 1/2 becomes a 0. 2 times 1/2 negative is -1. -1 plus 1 is 0. So we get a 0 over 0, right? So we have to do some kind of algebra to get out of this little trick here. And in order to do that, basically what I'm going to look at is factoring. I think I'm going to try and factor this. So I'm going to go ahead and do the limit as x approaches a -1/2 of, I'm going to pull out a negative x from the top right there, right? So I'm basically taking this and factoring it. If you pull out a negative, then it leaves a 2x plus 1, right? And we've got a 2x plus 1 in the bottom as well. And look at that. These guys cancel. Boom, boom. Leaving us the limit as x approaches -1/2 of just a simple negative x, actually. And so just a negative x is all that's left over. Just this guy. All right. And so we're basically now plugging in the limit here. And so this, we can just skip straight to it. And it's a -1/2, or obviously a +1/2. That is our limit. This would be the old limit if it were +1/2, and here it's if it were -1/2. There we go. We'll put in part 2 of this and in a bit.